Some functions are very complicated and difficult, perhaps impossible, to measure actually measure. And when we come across these situations where we can't actually measure a point, often we can use a approximation. We're going to talk about linear approximations because this is the simplest and therefore a great place to start. But the whole idea of this section is that we are making approximations about functions and points on that function that are very complicated and require lots of calculation, or we can't find, so we're just going to approximate them. And it turns out that in economics, as well in the hard sciences, we often turn to approximation rather than the actual calculation itself. So here is a function, f of x, the curvy thing, and we've got a tangent line associated with the derivative f prime a. So that tangent line has a slope that's equal to f prime a. Right? That's because this is the point of tangency there where the blue dot is, and we've got a on the x-axis. Now we can use the tangent line to approximate points along f of x, other than at point A. So for example, we might be interested in the point x. And if I draw this dotted line all the way up, this is going to give us something close to f of x. But you can see that the actual f of x is below the tangent line. So this form of approximation, and our approximation is this point right here, is sometimes called walking along the tangent line. And to help you visualize that, you can look at a little stick figure as they're walking from point A to point X, and walking along that tangent line is giving us an approximation of this point right here, this actual point. So there's a little bit of intuition. We'll go over it again in some more detail later after we've done some work, done some examples together. Why would we ever want to use this approximation? You can see that there's an error here. There's a difference between the actual and the approximation. Why would we ever do that? Well, maybe for some reason this actual is either a lot of work to calculate or we can't calculate it. So just say it's hard to calculate this. So maybe we want to approximate it. Now, how do you calculate a linear approximation? Remember, we want to use that tangent line. We want to walk along the tangent line. And it turns out it's just a formula. So if we're looking at approximating, right, this sign here, the wavy equal sign, that's an approximation. If we want to approximate f of x, this thing here, then we have a formula to help us do that, and the formula is right here. So this is the slope of the tangent line when x is equal to a. This part here, this is the change in x. And we can think of this point here as the Well, we can think of it as the starting point. Or known point. It's the point we're going to use that we have some information about, so we know what the tangent line is at that point, and then we're going to use it to estimate f of x, or approximate f of x. The question is asking us to approximate f of x, and we're going to do that with a linear approximation, because that's all we know so far. And we're given the change in x, and then we're being asked to compare our approximation to the actual f of x. So we know that f of x is approximately equal to f of a, the point that's easy to calculate, or a point that we know, plus the derivative f prime of a, so that's the slope of the tangent line at point x equals a, multiplied by the change in x, which is x minus a. So that's the notation that we're using. When I look at this problem, I'm going to define each component. We know that f of a is equal to, well, x to the 1/3, which is equal to 1 to the 1/3. So this is a, the original x, the starting point. Similarly, this is going to be our x value. And I know that f prime of a is equal to, well, the derivative of this function, f prime of a. So I'm going to start by writing 1/3 x to the negative 2/3. Or, no, I guess we'll leave it like that. You see I've taken 1/3 minus 1. That gives us negative 2 to the 2/3 as the exponent. And then if I replace x equals 1, because we're interested in a is equal to 1, we're just left with 1/3 times 1, which equals 1/3. And x minus a is going to be equal to, well, I've already told you what x is, 1.03 minus 1.00. And so x minus a is going to be equal to 0.03. There are the components. That's how we use the formula. Now all I have to do is sub in the values. And forgive me how wiggly my equation line is. F of a is equal to 1. Plus the slope, f prime of a, that's 1/3, multiplied by the change in x, x minus a, that's 0.03, and the approximation is 1.01. So if you're able to follow that, that's how you find the linear approximation. Now, what is the actual? F of x is actually equal to, well, it's equal to f of x, right? X is equal to 1.03. And if I use my calculator, I end up with 1.0099. And that's the actual. So the hard-working little computer calculator calculates it as 1.0099. Maybe we don't have a calculator, right? And without a calculator, we're able to get a really nice approximation just using our more limited human minds. Let's do this example together. I'll be honest, this one, when I read it, I know that the answer is true, and I always find the way that it's written in the textbook is confusing. So let's go over this one together. We've got f of x is approximately equal to f of a plus f prime of a x minus a. So that's the formula you're going to use to do a linear approximation. Now, how can I use a linear approximation to answer this question? Well, let's break it down into parts. So f of a is equal to log 1 plus x, and a is equal to 0. So the question's not quite as explicit as maybe I would have liked. And so we have log 1 plus 0, and we know that's equal to what? That's equal to 0. F prime of a is equal to, well, we're going to take the derivative of this thing here. And the derivative of that is 1 over 1 plus x, which is equal to 1 over 1 plus 0, which is equal to 1. So you always want to take the derivative before we sub in an actual value for a and x. And in this case here, just to be clear, x is equal to a. Right? And that's why we have the a right in there. And what's x minus a? That's just equal to x minus 0, which is just going to be equal to x. So now we're ready to put this all together. F of x is approximately equal to 0 plus 1. Remember, I'm just following along this expression up here. Plus 1 multiplied by x minus 0. I'll just put in the minus 0, make sure you remember what I was doing here. And you can see that we're just going to be left with x. And so log 1 plus x is approximately equal to x, which is handy. So we often have things plus 1 in economics. Maybe because I study finance, I see a lot of growth rates. And growth rates, we often have the 1 plus the growth rate so that we maintain the base, show that it's growing. So the ones are often, there's often a lot of ones floating around, and it's nice to be able to approximate those ones away if we end up with the log of 1 plus something else.